Hello, my name is Emma Ryan, and this summer I worked on the test stand hardware upgrade. This is through the Department of Physics with Professor Laura Jeanty and help from Andre Kabanda and Tim Matthews. Research question and background. This what Professor Jeanty's group works with is a part of the ATLAS experiment, which is a high energy physics experiment. These experiments question how the smallest parts of matter interact and if we understand it correctly. And they also ask questions like, what is dark matter made of? How does it interact with everyday matter, and how do we detect it? The way that ATLAS does this and many other high energy experiments do is by colliding particles together and seeing what comes out in the collision. At the Large Hadron Collider at CERN, there are proton-proton collisions. Detectors like ATLAS are used to track position and energy of all of the particles that come out of these collisions, and using that, we can analyze them and see if we understand them. In a couple of years, the LHC is going to be upgraded to have many more collisions, which means a lot more data for our detector. So ATLAS is going to upgrade with it. As a part of this, Professor Jeanty's group works on the data acquisition process. So how data gets from the detector to the computers. Test stands, like the one here in Oregon, are used to test this process and make it better, make sure we understand it. This summer, I began to upgrade ours to use much of the same technology that they use in ATLAS. So everything in the blue box on screen I worked with and I set up or helped set up. Already there was the RD53B, which is a pixel detector, a sensitive set of pixels that record a hit whenever a charged particle passes through them. There are layers of them in the detector, and they're used to track particles, track their position. Ours is on an SCC, a single chip card, which is just one pixel detector in that yellow box there. In ATLAS, they're arranged with multiple detectors per chip. This was already here. It was used in the old setup. It's not the exact model that was used on ATLAS, but it's pretty close. First step was setting up the server for Felix. Felix is used to interpret and handle data coming in from the RD53B. It is a field programmable gate array, which means it can be reprogrammed after it was made to handle different scenarios. So depending on your exact setup, it will be able to adapt. At the beginning of the summer, we got this computer server delivered with Felix installed inside of it. I made sure it could turn on, that it had all required firmware and software downloaded, and that had SSH enabled so people can access it remotely. The next question I needed to figure out was what parts we needed, because the data from our chip card can't go straight to Felix. Felix uses fiber optic connections, and our SEC uses an electrical cable. So we needed some way to switch between those two, and that is the VLDB board, the Versatile Link Plus demonstrator board. So in order to connect that to Felix, I needed to find the correct optical cables, and I also need to figure out the electrical side from the SCC to VLDB. The electrical side, the DP to DP mini cord, which is from the SCC, connects directly to the breakout board. Originally, I thought this was going to be more complicated, but it turned out simpler than I expected, which was great. A breakout board which you can see here, it's basically a fancy adapter. It can take in multiple inputs, but we only need one, and it connects directly to the VLDB. The VLDB converts an electrical data from the SEC to optical data that Felix can read. It's part of a larger project by both ATLAS and CMS, another experiment at CERN, to create radiation-resistant optical connection systems. The two biggest parts of this are the Versatile Link Plus transceiver, or VTRX Plus. It's the fiber optic connector that goes to the cables. If you see the little blue loop on that picture, that is what that is. It's also in the lighter yellow box. And then the low power gigabit transceiver, or the LPGBT, it's what does the converting. It's a radiation tolerant chip made to handle high-speed optical data transfer. And it's used for data acquisition, timing and trigger control, and slow control, which are just all these different types of things that we need to do. It can be used as a transmitter to send out data, or a receiver to just receive data, or a transceiver, which is both. So it has to be configured first to work properly. Next on the list are fiber optic cables. Felix's fiber optic connector, which is in the bottom picture, is an MPO24, which is 2 rows of 12 fiber optic cables, which if you look closely in that picture, you can see them. The fiber optic cable on the BLDB Plus is an MT12, which uses an adapter to connect to an MPO24, MPO12, which is just a 12 fiber optic cable. So to connect these two endings, we need two breakout cords that split up all of the fibers to different endings, so then I can connect the correct fibers together. The connectors on the breakout end are LC endings, and I'll use an LC to LC adapter to connect them. So I researched, I found all of this out, and then I had to order these cables. And then they took a month to come. So while I was waiting, I worked with YAR, yet another rapid readout. This is the software that we use to run scans and get data from the RD53B. I installed it on the Felix computer by cloning it from the Git repository, and YAR runs scans, which is it injects a certain amount of charge to each pixel and record the time over threshold TOT value, which corresponds to the charge of that. It corresponds to the charge that was injected. This should be very similar for a given charge for each pixel, and so by doing this, we can tune the pixels to different TOT values to make sure they all match up. And all the pixels aren't activated at once, but in batches over a series of loops. Because the single chip card wasn't connected yet, I couldn't run actual scans, but Andra had developed an emulator which mimics having a type of pixel detector on the other end. And so this is a scan that I did trying to figure out what the different loops were and how it worked. Also, while we were waiting, I started to configure the LPGBT because we needed to tell it what we wanted it to do. The VLDB Plus came with a PIGBT controller, which is how you work with this. It's based on Raspberry Pi, and it uses a web interface to configure each setting. And Andra has worked with these before, and so he sent me a configuration that I then loaded on to the website, which you can see here in these screenshots. And then the fiber optic cables came, which was great. The fibers have arrived. So we connected everything according to my original plan that I had pieced together from different reports of other people doing this, and it didn't work. So currently I am trying to figure out why it didn't work and talking with Andra and figuring out what we need to do next. How do we fix this? This is a large picture that I have drawn over of my entire setup. So we have power supplies on the right, and then you can see the PIGBT, the BLDB Plus, the breakout board, and the RD53B, plus a temperature monitor that I set up at the end of spring term. And you can see I have drawn on the fiber optic connections to the Felix server. The fiber optics don't actually look quite like that, but because it's difficult to get the entire thing in one picture, this is what I did. So the next steps are troubleshooting the fibers, figuring out which transmission and receiver channels need to be connected, and check which fibers on the VLDB Plus end need to be connected. In addition, I'm doing more work with YAR. I am modifying the code so that it doesn't crash when the wrong scan file for the chip is used, and instead just pulls up an error. And that is what I have done this summer. These are some of the references I used. I looked at the YAR docs a lot. I looked at the VLDB Plus manual a lot. I looked at the LGBT docs a lot as well. So yeah, thank you for watching.